Hello everybody, and welcome to this afternoon session about fractional partial differential equations and applications. The aim is to show latest developments in this theory. Our first speaker is Joel Restrepo. Currently, he is a postdoctoral researcher at Nazarbayev University in Kazakhstan, and he is working on fractional calculus among other subjects. Today, you will talk about direct and inverse Cauchy problems for space-time fractional differential equations. Joel, the stage is yours.
Okay, thank you very much. Hello, everyone, and really appreciated this invitation for the organizers of this special section. Well, I put here direct and inverse Cauchy problems, but today is better. I mean, there is not too much time, so we are going to discuss just direct. Okay. So the plan is, okay, let us speak about the fractional calculus a little bit, just some introduction for people maybe like they don't know about this. What is the motivation of our work? And then what we did, what is open, and what we expect like people maybe be interested in the future. So in general, what is the fractional calculus? It's just a simple thing. It's just to generalize the order of differentiation and integration, any number, whatever you want. This is the main idea, simple one. So what is the main point for fractional calculus is this well-known formula. Like if you integrate n-fold times one function, so you can get in the other side this closed form where, look, the n times integral depends of the order in the other side, you see? So it's normal to think about what happened if we put just alpha, with alpha any number. It was the first approach. And it was given for Riemann and Liouville. I put RL, but it's Riemann Liouville. And we have just, they just introduced this operator at the first stage. Later, we are going to, if it is necessary to speak about the boundedness or all this stuff about a system, it was another, is another thing. But at the beginning, this is the operator, like they introduce as a generalization of the normal root, like we can see at the top. So look, here we have just alpha in 0, 1, but we can extend this to any number. Just fair approach to anyone to see what is happening. And then after they introduce this, they ask themselves like, what is the inverse operator of this? What is the, like we can say in this moment, like the fractional, or what is the inverse operator of this? Like it will call the fractional derivative. Like we did in in normal calculus, we have one integral, the derivative we can derive, use the well-known calculus theorem, and we can recover the function. Here is like the same. So the inverse operator they call the Riemann-Liouville fractional derivative, and if it is proof like has this form. Look, the derivative is outside, as you can see, and here is the power of the function is minus alpha. Here we are just again, as I said, alpha in 0, 1. Look the following. When we want to introduce, I mean, in further studies, we can introduce the derivative inside and see like, okay, what happened with that operator they call Kaputo. Nevertheless, it was like also known that result before, like you can put inside the derivative, because from this one, the Riemann-Liouville fractional derivative, we can get that. So look, when we refer here in this talk about the Kaputo, it means like the derivative is inside, and we have such a power inside to the integral. This is the main approach to fractional calculus to a little bit understand what is going on. Here we have some inverse operation between derivative and integral, but I'm not going further to this. We don't have too much time. So some classical sources, we can see this Sanko, Kilbas, Marichev. This one is more recently, to say more recently. And another one, a good introductory textbook is this Million Rows, like anyone can see. Okay, let us start with what is the motivation of this talk. Look, at the beginning, there were several researchers studying this multidimensional fractional diffusion wave equation when this A is 0. So the idea was to try to find the fundamental solution, the explicit fundamental solution of that such a problem. Later, also they asked what is the fundamental solution of the time fractional telegraph equation when A is more than 0. Here we have like X is in Rn, T more than 0. And at the beginning, we have like alpha in 0, 1, beta in 1, 2, and this is some constant, and this is the Laplacian. Delta X is the Laplacian. This is the delta Dirac function, this the distributional one. So the question is, what are the explicit solution of this such equation? Of course, there are some good things about this operator is that when we have beta 0 here in this operator, we have the Helmholtz operator. When we have a beta 1, we can recover the heat operator. This is very general operator. And when we have this beta equal 2, we have the weight operator, you see? So this is very general one still here in this stage. And some first words can be found in these two papers. There are many people working in this, but I just wanted to say some of the some of the people is taking into account too much, but there are many words in this direction. So recently, the solution of these guys were not so explicit like people wanted. So more recent works were done by Lucho, by the way, Ferreira, Vieira, and even Rodriguez with some other papers. But what they did, they gave their solution by some special functions. In several cases, this is very, very explicit, and you can work and deal with it with that in more numerical stuff and some other things better than the before previous ones. So the first question about what happened with this operator of this type of fractional Cauchy problem for Riemann-Liouville in Kaputo time is already done, as we can see. But of course, there are some other open questions here, like what happened with some other operators more general, like a Pravka, for instance, and some other maybe singular, no singular operators, like maybe you can apply here. Try to get explicit solution. This is the challenger here. Try to get like a formal solution. This is the most difficult part here. And with this question, again, what is the solution of this type of differential equation? It is done for Riemann-Liouville and Kaputo fractional operator, but still there are open questions for some other type of differential fractional differential operators, like a Pravka. I mentioned Pravka because it's a very general one, and it becomes to the Riemann-Liouville in particular. So look, to solve such a problems, the normal approach it's very simple, is to apply the space Fourier transform in Rn. Then we get a fractional initial value problem with constant coefficient. So we can use the well-known results by Lucho when he already gave a closed solution for that for that type of fractional equation. And then again, we use the inverse Fourier transform. Here, the most difficult is interesting is like how, when we apply this inverse, we can get and recover good explicit solution. This is the most challenging thing. So our question, in my words, in the last 2 years have been like, okay, let us analyze a bigger, huge problem. What happened with this general problem when all these are different fractional derivatives and we have different constant coefficient? Again, the main problem is to get some closed solution. We can use here again the work of Gluchko, but there is still one gap, how to get the inverse Fourier transform of this special function, how to get this in a explicit form. Now I'm working on that, but still this is was the main question. And there is another one, like what happened with variable coefficients? This is still under study, but this case is not well known and it is open for research. I mean, there are not many words in that direction, but it is like still a new direction to work on that. So let us discuss this in a bit. So again, we are gonna, what is the first approach to get this is like we are gonna to use the same, like it was already used, first to apply the space Fourier transform, and then we will get a fractional differential equation with variable coefficients. So our problem is translate to solve a fractional differential equation with variable coefficient. So this is the second step. Now we are not asking about the solution of that Cauchy problem. We are asking about the solution of variable coefficient fractional differential equation. In this field, there are not many words, but still we try to prove different. I mean, there are some words on that field, but we try to prove with some other type of operators fractional differential equation with variable coefficient. So for instance, here in this paper, we use, in the first one, we use fractional differential derivatives with respect to function. This is a general one. And in the second paper, we use Hilbert type, but with respect to function, general operators for that. Why? Because we know, like, if we know the solution of such a equation, we can use in Cauchy problems still. So after that, we can then get the solution by applying the inverse space Fourier transform. Still, some open question here because there is not a very good closed form like I wanted, but still there is the inverse of some kernels involving some fractional integrals. For instance, in a simple case, this is a very good space, like n derivatives is n0 minus 1 derivatives of this function in order t, and the fractional derivative is also continuous. So we can get this solution. Look, this Wj is initial conditions, but here in the last in the second part we have the inverse Fourier transform of a very like I say some kernel, like is not explicit. This is the new challenger now. Try to get some explicit solution of that. In this paper we prove some things like for heat and wave equation, this kernel becomes the same solution in the normal one, but still is open question, and we are trying to look how we can get more explicit and better form. Okay, just to finish one example. Look, this we have this initial value problem, weight type, beta is 1 and 2, and this is a variable coefficient, this t in order beta 0, because we can calculate explicitly. So look, the solution. The solution is given almost explicit, but here we have the Fourier transform of this Mittag-Leffler function of Kilbas type. This is a different one, and we cannot use this. We cannot change this better because there are some problems inside. Here, the good thing is like when we have beta 0 tending 2, and the variable coefficient, this t in order beta 0 is 0. So we obtain the classical way equation in Rn. So both solution coincide. Well, I think like my time is over, so thank you very much.
Thank you very much, Joel.
Sorry for the last thing because I didn't have time too much.
We have still 3 minutes, so.
Oh, 3 minutes.
Yes.
Okay, that's very good. So I can just say here something.
Okay.
Look in this example when we are trying to figure out what is happening in this inverse. Look at the inverse Fourier transform. Here we have a special function. This is metal level of Kilbas type. So when you want to try to get more explicit, I mean, try to change this for this, like in Sanko Kilbas Marishev they did. Change this radial function with some other function with the Bessel type and integral 0 plus infinity. It were good there, but in this type I couldn't do, and still we are trying to get some better solution. But this is the main challenger here, and we will see what is happening. Still working with some other people in that problem. Even with numerical stuff, we are trying to see what is going on. But we hope like people will be interested in this new open direction with constant, but with variable coefficient. So this is an invitation for anyone to try to see what happened here, guys. And again, thank you very much.
Thank you, Joel. I have one question here in the chat.
Yeah.
What is the physical meaning of this kind of problems, since we know that the standard time fractional diffusion equation is useful to model anomalous diffusion problems?
Yeah, well, this is for instance, this type of problem with, you mean with constant coefficient or with variable coefficient?
Well, both, because they are generalizations of the usual one.
Okay, look, at the beginning, someone was asking me somewhere some question about how he can solve this, because he was stuck in a problem like he was doing in engineering things. So at the beginning, I was like, well, guys, this is maybe done for someone. He was speaking about just one variable, just one different one variable coefficient. So I said, I mean, as a mathematician, I have to do the more general thing. This is the other point. Like as a mathematician, I did the more general thing, but still, some people, they are trying to use with just with one constant coefficient, two constant, for instance, with one variable coefficient, or it depends of the problem. But still, look, as I said, it depends of the people. As a mathematician, I must try to do the general ones. Of course, trying to get some explicit examples and solution. It is now my.
But at least this motivation comes from a physical problem.
Yeah. I mean, yes. it was came for something, but look, I wanted to solve just for two, yes, because if for beta for one variable coefficient. But later I said no. Why I must solve for one variable coefficient? Let us solve for the general case. So sometimes this is what the people don't understand. We gave the main tools, but they must apply in their cases. You see.
Okay, but that is the usual. Okay,
yeah,
so
I mean,
thank you very much.
Thank you.
Let's pass to our second talk from Nelson Vieira from University of Aveiro. I and Nelson have been working together in the last years on topics about fractional calculus, and today he will speak to us about the time fractional telegraph equation of distributed order.
Can I share, Milton, the slides?
Yes.
Yes? Okay. Can you see now?
Yes, we are
Okay,
seeing.
perfect. Now it's better. Okay. So, thank you for the introduction, Milton. It's nice to present in this national meeting of Portuguese Mathematical Society, one of our recent works in fractional calculus. Today I will show you the results from one of our recent papers about the time fraction telegraph equation of distributed order. I will try to make an overview and present the main steps that you can find in our paper. In the end, I will indicate you the main reference, and for sure I will skip the several details, and there you can check with more detail and more carefully all the justifications for the calculations and the deductions. So, an outline of the talk. First, short indication of the motivation, some basic reference about this topic. Then I will present the time fractional telegraph equation of distributed order. Namely, I will make the formulation of the problem. I will present the solution in the Fourier Laplace domain, and then we will invert the integral transforms and obtain the expression, the explicit expression of the integral representation of the solution in terms, as we will see, as Laplace integrals of Fox H functions. We will see that, and we will see that also convolutional integrals. We will have a representation of our solution in the time-space domain. In the third part, I will indicate some particular cases that we study. Then a short remark about the fractional moments of the first fundamental solution. And then the main results when we apply the Tauberian analysis for the second order moment. For only one of the particular cases that we study. Then the conclusions. I hope I have time to show everything. Let me know, Milton, if I pass the time. Okay. So why we consider this type of fractional differential equations? Because fractional partial differential equation of distributed order are related with physical process in mobile time scales. For example, fractional kinetics, Cauchy problems of time fractional diffusion wave, generalized time fractional diffusion, time fractional reaction diffusion equations, fractional subdiffusion equations, and just to mention some of possible connections between this type of equations with physical process. Some basic and important reference, most of them in the one-dimensional case. We have the work of Mainardi and his collaborators. We point out the connections they established between the Fox, between this subject and the Fox H function, via the use of integral transforms such as Laplace, Fourier, and Melik transform. We have also the work of Shekin and also his collaborators. They study the properties of the diffusion equation with fractional derivatives, fractional distributed order for the description of anomalous relation and diffusion phenomena, the subdiffusion and superdiffusion process. We have the work of Gluchko and his collaborator. He considered the time fractional diffusion and wave equations of distributed order in Rn plus R plus. Moreover, they establish a connection. They show that the first fundamental solution can be understood as a spatial probability density involving in time. Also, they consider boundary value problems and study the maximum principle for the generalized time fractional diffusion equation. Moreover, we have the work of Tomovsky and Sandev and their collaborators. Namely, they made an investigation of the solution of the generalized distribution or the diffusion equation with composite time fractional derivatives, also by using Fourier and Laplace transform methods. So, what we want to consider, we want to study this time fractional telegraph equation of distributed order. We have here the one derivative with order between 1 and 2, a derivative with order between 0 and 1, the classical Laplacian operator in Rn, and we have given these density functions V2 and V1, positive density functions. We consider the following initial and boundary conditions to our, in this case, in our problem. The time fractional derivatives are in the Kaputo sense. I didn't put here the expression because I was on the time I was short of time, but it is in the Kaputo sense, the fractional derivative. So what we can do to obtain the solution in the Fourier Laplace domain? We have our strategy consists in the application of two integral transform, like it is usually done in the literature. We apply the Laplace transform with respect to the variable t, and then we apply the Fourier transform, the n-dimensional Fourier transform with respect to the variable x, and applying these integral transforms, taking into account the boundary and the initial conditions, we get this representation for the solution in the Fourier Laplace domain, where here we have the Fourier transform of the function f and g, and here we have the Laplace and Fourier transform of our function q. Moreover, these quantities capital B2 and capital B1 are given by this expression. It is important to observe that this expression does not come directly when you apply the integral transforms. You need to manipulate the expression, isolate the terms, and then after some calculations, you get this representation for the solution. Now, we can say that the easy part was the previous one, was to obtain the solution in the Laplace Fourier domain. The difficult part is to invert these integral transforms and obtain our solution in the time space domain. So, what we do? To invert the Laplace transform, we apply the Differential theorem, and then to invert the Fourier transform, we apply the Mellin transform, which is very interesting. To invert an integral transform, we will use another integral transform. The Differential theorem tells us that under certain conditions that are fulfilled in the case that we study in our paper, we can interpret the inverse Laplace transform as the Laplace transform of the imaginary part of this function, where s is substituted by this quantity r times e to the power pi, which is the branch cut point of the functions. So what we deduce this representation for the solution. Here we already inverted the Laplace transform. This expression, these quantities K1, K2, and K3, K1, K2, and K3 are given by this expression. And how they appear? They appear when we start to analyzing these three terms, and we need to introduce auxiliary functions, and then the process of extracting, in some sense, the imaginary part of the several terms, lead us to these quantities Q1, Q2, and Q3. The expression for these quantities are given by this one, by this. Here, there are another quantities A and B, which are given by this cosinus and sinus, and the radius of what of the quantities V2 and V1 that we defined previously. What we can see now, it is clear that comparing with the already known works in the fractional diffusion case and wave case, since we are dealing with two quantities, two derivatives, the calculations are much more complicated. We have more terms, and the number of quantities that appear in the solution increase. Now, the next step is to invert the Fourier transform. We apply the inverse Fourier transform, the n-dimensional. We take into account that we are dealing with radial functions, and this fact allows us to use special integrals or representation of the inverse Fourier transform for this special situation. And as we will see, we have our solution in the time-space domain as a convolution integrals. Here we have the convolution in x and t. And what we need to do now, these integrals in color appear from the process of inversion of the Fourier transform and the application of the formulas that we know for the radial case. And what we need to make now is to calculate these integrals, E1, E2, and E3. How we do that? We use the Mellin transform. Each of the integrals can be interpreted as the Mellin convolution of two functions, gi and function f, which is equal for all the three integrals. The function f involves the Bessel function, and the G1, it's the quantity, it's different from each one of the integrals. To calculate this Mellin transform, this is the most technical part of the work. You need to make a change of variables. You need to rearrange the expression of the integrals. You need to use integral formulas from the books from Prudnikov. So it is a technical and tricky process. The calculation of these Mellin transforms and then the Mellin convolution. Making these calculations, inverting the Mellin transform, we cannot forget that each of the integral is a Mellin convolution. So after the calculations, you need to invert the Mellin transform. Making the inversion, you obtain a representation of the integrals in terms of Mellin-Barnes integrals, and this last one can be interpreted as Fox-H functions. And this is what you get for the first integral, and we denote for have a short notation and a little bit more short expressions. We denote this h function in blue color, this another h function it's in magenta color. We have these quantities, this quantity psi given by this expression. The expressions a and b are given when we make the inversion of the Laplace transform. Proceeding in the similar way to the second integral and to the third integral, we obtain these representations, these expressions for the integrals. We cannot forget that these quantities in color represent Fox-H functions. And then making the combination of all these results, we get the main theorem of our work, which tell us that the solution of our problem is given in terms of convolution integrals by this big expression, where the functions G, the fundamental solution G1, G2, and G3 are given by each of one by this. What we have done here, these expressions are the expressions that we have here, but we substituted E1, E2, and E3 by the correspondent results that we obtained by the Mellin transform. And what it is important to observe in our result is that, as it is, the expression is quite complicated to implement, and even numerically, if we want to do that, we need to make we need to make an asymptotic study of our expression, especially in the parts related with the Fox-8 function. But what I want to tell you is that this expression can be interpreted as a general expression. If we consider particular cases of our big equation, the expression of the solution becomes much more simple in the form and in its implementation. For example, in our paper, we consider the case of the eigenfunctions of the time fractional telegraph, diffusion, and wave equation. And also we obtained the solution of the time fractional wave equation of distribute order. So we are, as I told you, we are talking about particular cases of the main equation. Now, what we can do in this part, what I want to show you in this slide. What I put here, what it was. As you can see in the solutions, we have these quantities A and B, and I remember you that, I will make short, A and B are defined using the quantities ρ1, ρ2, gamma1, and gamma2, and they are obtained by the integrals B1 and B2. And the quantities, the capital B1 and B2, are obtained from the density functions. Let me see where they are here. So what we show in this part of the work is which it will be the form of the quantities, these quantities, ρ2, gamma2, ρ1, and gamma1, for some particular considerations of the density functions. I put here the case of the single order, how it becomes these quantities. We also presented in our paper the multi-order case, the uniform distribute case, the linear density case, the sinusoidal case, and the exponential case. And these allow us, the way as we constructed the solution, you can consider, in some sense, mixed cases. What I mean, you can consider, for example, a B1 of single order type and a B2 of exponential type, or any possible combinations. Just to end, some connections with the probability. Fractional moments, making a reinterpretation of the Mellin transform, we can deduce the expression for the fractional moment of arbitrary order in the Laplace domain for our first fundamental solution. We have these special cases that we can deduce from this expression, the mean value, the variance, and the third moment. Considering the second moment, the variance, and making a separation, just to simplify a little bit the physical interpretation of the situations between the diffusion and the wave case. For the diffusion case, the second order moment, the expression became a little bit shorter. A first remark for the three-dimensional case, our moment does not depend on t, it's a constant function. If we consider the particular case of the slow diffusion process, capital B1 will have this expression, and then substituting this in here, we have this expression for the second order, which has this behavior when s goes to 0 plus. The Tauberian theorem allows us making the inversion of the Laplace transform to understand the behavior of the second moment when t goes to infinite. So making the inversion of the Laplace transform using the formulas that you can find, some of them are very easy, some of them you need to use or the book of Prudnikov, for example. So you get these expressions when t goes to infinite. When n is equal to 1, you recover all the results that you can find in the literature. We have a different behavior dependent on the dimension where we are. And we point out this restriction, this upper restriction to the parameter alpha 1 that we have for higher dimensions. For the when s goes to plus infinite, you can also obtain an expression for the behavior. You can apply the Tauberian theorem to understand the behavior in the time domain when t goes to 0 plus. Also, the conclusions from the analysis of the expression are in some sense similar to the previous one, in the sense that we have different behaviors dependent on the dimension. Other situations that we studied in our work, we studied the super slow diffusion case, when B1 is a constant, it's of the form 2 alpha or of the form P2 sinus of alpha P. And we applied also the Tauberian theorems. Just one graphical representation of the moment of the slow diffusion process when t goes to 0 and when t goes to plus infinity. For alpha 1, 0.75. As we expected, the behavior differs from in the different dimensions. When equal is 1 or 2, the variance increase. When n is equal to 3, we have a constant behavior. When n is equal to 4, we have a decreasing behavior. For the wave case, we can do a similar approach, obtain the simplified expression for the moment.
Finish.
What, Milton?
You have to finish, Nelson.
Okay, so you can apply the same analysis, obtain a similar expressions. You can obtain the graphical representations, and the highlights I explained during the talk. This is where you can find most of all of the details in the calculations and in the analysis. Is a paper that it is in press in Communications in Nonlinear Science and Numerical Simulations. Thank you for your attention, and I'm sorry for the delay, Milton.
Thank you, Nelson. Since we are out of time, I ask that if someone has questions, put in the chat. Okay, I have some questions here, but okay, just 1 minute. Nelson, if you can ask in 1 minute. On those particular cases of weighting functions, are you able to conclude anything about the smoothness of the solution or smoothness properties?
We didn't make this study. We only saw the form of the quantities, as I told you, rho 1, gamma 1, rho 2, and gamma 2, but we didn't see what was the consequence of putting this expression inside the big expression of the solution.
Okay, I thank you, Nelson, and we move to the third lecture.
Okay, I will stop to share. Now it's my turn, Milton, to present the next talk.
Yes.
So you are the next one. The next speaker in this session is Milton Ferreira. As he told previously, we have worked in the last years, Milton, myself, and Manuela in fractional partial differential equations. It's with a great pleasure that I present Milton, and I will not delay anymore. Please, Milton. He will speak about Dirac operators in higher dimensions. So please, Milton, start.
Okay, I have a slight problem here. So okay. I think you can see now my presentation. So I will speak about the interplay and connection between time fractional calculus and operator calculus in Clifford analysis. This is a joint work with Nelson Vieira and Manuela Rodrigues. And first I give a brief motivation, then I define the notation for the fractional derivatives and some notions about Clifford analysis. Then I will present the fundamental solutions for the time fractional diffusion equation and for the time fractional parabolic Dirac operator, together with the LP integrability of these fundamental solutions. And in the last session, I will present the main results about operator calculus, namely time fractional Stokes theorem, time fractional Borel-Pompei formula, and fractional Theodorescu and Cauchy-Bitesides operators. So the time fractional diffusion equation has been already seen in the last two presentations. It is connected with the non-Markovian diffusion process with memory. In probability theory, it is related to jumping process, and it is well known that it models the anomalous diffusions exhibiting subdiffusive behavior. In other way, the Clifford analysis. What is Clifford analysis? Is the higher dimensional theory that generalizes the complex holomorphic function theory in complex analysis. And Clifford analysis proved to be a good tool to study partial differential equations of mathematical physics. For instance, the work of Grubek and Sprosig was applied to a large type of equations, for instance, Lamé equations and Maxwell equations. For the case of time-dependent problems, we refer here the work of Sergeira, Scheller, and Solman, who studied Navier-Stokes equations using tools from Clifford analysis. So the aim of my talk is to present you the fundamental solutions of the time fractional diffusion wave and parabolic Dirac operators in arbitrary space dimension, and show how to develop a time fractional operator calculus. So just to fix the notations, the left and right Riemann-Liouville fractional integrals are denoted by these symbols here, are convolution type integrals. The kernel is of power law. In the left case or upper case, we integrate from A to T. And in the right case or backward, we integrate from T to B. And we can construct and define the left and right Riemann-Liouville fractional derivatives that I denote by these symbols here, which are nothing more than the differentiation of order m, and m is an integer, of the fractional integral operator. So is the composition of these two operators, the fractional integral and the derivative of order m, where m is the integer part of beta plus 1. Since this is like an interpolation operators, so they interpolate the integer derivative. So in the case beta is an integer parameter, we recover the integer derivatives. In the case of the right or backward, it's up to a sign. For the left and right Kaputo fractional derivatives, we reverse the order of the composition of the operators. So first we differentiate the function m times, and then we apply the fractional integral operator. By ACM, I denote the class of functions which are continuously differentiable on the interval AB up to order m-1, and the derivative of order m-1 is absolutely continuous on the interval. And the first result that you can find in the literature is about the boundedness of the fractional integral operators. And for a beta between 0 and 1, and p greater than 1 and less than 1 over beta, it is well known that these fractional integral operators are bounded from LP into LQ, where Q is related with p and beta with this equality here. About Clifford analysis, let me only give you some definitions. We consider the n-dimensional vector space Rn, and do with an orthonormal basis, E1 until En. And we define the universal real Clifford algebra R0n as the 2 to the power n dimensional associative algebra, obeying these multiplication rules between the basis elements E1 until En. So we have, each time we multiply Ei, Ej, with I different from J, the anti-commute, so the product is equal to minus Ej, Ei, and the square of each of these elements equals -1, so this acts like imaginary units, like in the complex plane that we have an unit imaginary. So this is a associative but non-commutative algebra. And one of the main objects studied in Clifford algebras and Clifford analysis is the Dirac operator. That is the sum of the partial derivatives in each direction multiplied by the basis elements Ej. This is a generalization of the gradient gradient operator when we apply to multi-vector fields, because we can, inside the Clifford algebra, we have a multi-vector structure. And this operator is important because it factorizes the Euclidean Laplacian. So if you make the square of this operator, it gives a scalar that is the minus Laplace operator. So there is here a big connection between the Laplace operator and the Dirac operator. So from the harmonic function theory of the Laplace operator, we can obtain several results for the Dirac operator. Well, in our case, we want to deal with time-dependent problems, and so we need to enlarge the space. So we are going to endow our space with two more basis elements, F and F dagger, that will constitute a base in Rn+2. These elements are constructed, F and F dagger are constructed from two new elements, E plus and E minus, with the following signatures. The square of E minus equals -1, so this acts like a space direction. And the square of E plus equals +1, so this acts like a time direction. And we make the combination between E plus and E minus and construct F and F dagger, so they are the diagonal of these two directions. And they have the following properties. The square of these two new elements, F and F dagger, equals 0. So they are isotropic elements and gives the character of parabolic algebra in our construction. There are more relations. and these new elements anti-commute with the previous basis elements. And we construct an operator of Dirac type that will allow us to consider problems with time derivative. And for that, we have here the Dirac operator. So this is the first order operator. So we have the Dirac operator. Then in the F component, we have the partial derivative in time. And in the F dagger component, we have a constant that can be plus 1 or minus 1. And this gives the character of the forward and backward derivative. And this operator, due to the properties of our algebra, is going to factorize the n-dimensional diffusion operator. So if we square this operator, we get the scalar operator that is minus Laplace operator plus or minus the time derivative. So this is the forward and backward time diffusion, diffusion operator. So as the multidimensional time fractional diffusion equation that I'm going to present here is this simple one. So we have a left Kaputo time fractional derivative of order beta between 0 and 2. So we consider the two cases of diffusion and wave, minus a constant and Laplace operator applied to our function. And we obtained in 2017 the first fundamental solution of this equation, satisfying the initial conditions given here. First, here as a Fox H function, so as an integral of contour type in the complex plane involving a quotient of gamma functions. And to be more explicit, if we compute this integral using residues, so we can obtain a series representation. We have done that, and we obtained two different situations. For n odd, we obtain this series because we have an infinite sequence of simple poles to compute. That's why we get a series. The first term is just a simple sum, and then we get this series. And for n even, since we have now simple and double poles, well, the fundamental solution is more complicated, and we get here in the series the d gamma function and also a logarithmic term. Well, just to give you an idea of the fundamental solution and how it evolves in time, you can see here in the dimension 1 the plots. In the first line, we have the fundamental solution from the case beta 0.2 to 0.9. In the second line, we have from beta equal 1, that corresponds to normal diffusion, until beta 1.7, and here you see the wave diffusion appearing. In dimension n equals 2, we made also plots. In the first row, you can see the diffusion. So these plots are models of x against the time t. And in the second line, you can see the diffusion phenomenon. Starting from the normal diffusion, beta equals 1 until beta 1.7. Dimension 3, we also made plots to see what happens, and one thing we can see is that the fundamental solution can be negative, so this is different along the dimensions. Regarding our time fractional parabolic Dirac operator, what we are going to do is to replace the time fractional, the time derivative in the classical parabolic Dirac operator with a fractional one, in this case of Kaputo type. And of course, this is going to factorize time fractional diffusion operator, now with the fractional time derivative. And this is important, this factorization property is very important because to compute a fundamental solution to this time fractional parabolic Dirac operator, we now have only to apply the time fractional parabolic Dirac operator to this fundamental solution, that is the fundamental solution that we obtain here in the scalar case. And we did that, so you obtain the fundamental solution for the parabolic Dirac operator with three components. Here, the first is the vector part in x, then the component in the direction f, and the component in the direction f dagger. For an even, it is also possible to obtain the expression. I show you here the explicit expression. And more important is to see how these fundamental solutions behave. So for the case of the dimension 1, we can write in these three right functions. We observe a discontinuity in the this is the vector, the real part here of the fundamental solution. You observe a discontinuity here that becomes continuous in the case of beta equals 1, and then again it becomes discontinuous. For the f component, we have this behavior in the case of diffusion and in the case of the wave. Well, about the integrability, LP integrability of these fundamental solutions, what we did, we took from this first paper asymptotic behaviors, the asymptotic behaviors of fundamental solution, and then we just integrated and we obtained the conditions for the integrability of these fundamental solutions for every dimension. And we have to separate in these three cases of the dimensions because the asymptotic behaviors are also separated in these different cases. The integrability you can see in this paper from 2009. These are the conditions for the integrability of the fundamental solution of the time fractional diffusion operator. And just to give you an overview of the last part, let's construct all the possible operators. So with the Kaputo fractional derivatives and Riemann Liouville derivatives and of left and right type. So all these are important for what we want to do. All these factorize some appropriated scalar operators. And in the case beta equal 1, we recover always the usual parabolic Dirac and diffusion operators. And first, and the very important result in this theory is to construct a Stokes theorem. Because in Stokes theorem, you want to relate the integration over a domain and with the integral over the boundary. And since we are dealing with time-dependent problems, let's consider C a space-time domain. So it's a Cartesian product between omega in Rn and this interval in time with a piecewise smooth boundary. So for given functions, AC1 in the domain and AC1 up to the boundary, we have this time fractional Stokes formula. And what is important here is to observe that we are integrating over our domain, and this involves two different operators. So if you start here with the Kaputo fractional operator, this will be of Riemann Liouville type. If you start here with this backward operator, this will be upward operator. So there is here a double duality relation between these two operators. And the integration over the boundary, you split in two parts. So this is the boundary over omega. And this is the integration over the top and bottom of the cylinder. And here it appears this fractional integral operator of order 1 minus beta. There are other versions of the time fractional Stokes theorem. So if you start with different operators, as I mentioned, you have different double duality relations. So these are all the four, well, here we have the other three cases that are possible to consider in this fractional Stokes formula. In the case beta equal 1, we recover the usual in Stokes formula. So everything is fine for now. And then what we need, what we do now for progressing is to put the fundamental solution in this, not this, but in this Kaputo, in this operator here. We put the fundamental solution U of this operator. And when we do that, and after simplifications, we get what is called the time fractional Borel-Pompeo formula. That relates the values of the functions with two other integrals here over the domain and over the boundary of convolution type, as we are seeing here. And moreover, if V now is in the kernel of this operator, so when we apply this operator to V gives 0, we get a time fractional Cauchy's integral formula, like we have Cauchy's formula in complex analysis. So the values of the function can be recovered just by integrating over the boundary of our domain with the fundamental solution in this way. We can define fundamental operators. The first one is the integration over the domain, that is what is called the Teodorescu operator, and the integration over the boundary, that is called the Cauchy bitesize operator. So here, writing in operator form, this is what says the Borel-Pompeo formula. And we studied several properties that are needed for these operators. For instance, it is well known in the classical case that this operator is the right inverse of this operator, and it's still true for the fractional case, with some restriction, of course. And we studied also boundedness and mapping properties of these operators that I don't have time now to show you. And in the end, it is possible to compose the LQ space of functions on the domain into other function spaces. The space, the first one is the intersection of LQ with the functions that are in the kernel of this Dirac parabolic Dirac operator, plus the second part that are the functions that are in the kernel of this operator, but with null, with vanishing values in the boundary, and also in some fractional suboverlap space that we have here. And since this is a direct sum, you can define projectors P and Q to project to each of the components of the LQ space. And just to finish, you can use these tools to solve a boundary problem. For instance, let's consider this scalar value problem for a given function g in this fractional suboverlap space with null values in the boundary. And using these operators T and Q, the solution can be written as the composition of these three operators, and these generalize the classical case. Just to finish, some reference, but I also present some reference along my presentation. And I thank you all for your attention.
Thank you, Milton, for your interesting talk. Is there any questions? We have time for a short question. I have only a short remark. Milton presented these results for the case of the diffusion wave operator, but we already obtained some for the case of the telegraph operator also.
Can I ask a short question, please?
Yeah. Yes. You can ask.
Well, both of you already mentioned some of my papers, and for sure I did something similar, but for much in the much simpler situation. So you consider now essentially more complicated problems, and respectively your solutions are essentially more complicated. So your solutions are in form of some operators like Laplace transform, inverse Fourier transform, for some very general special functions. And then my experience with solutions of this kind is that very complicated special functions or solutions in terms of very complicated special functions, they are objects in a sense for themselves. So it's very difficult to find some applications of these solutions. And therefore I wanted to ask you if you found some consequences, some useful consequences from your very general solution formulas and integral representations for the solutions for these very complicated problems.
Well, in this particular study that I present, we were interested in try to fractionalize a theory that already existed about using Clifford Analysis related with operator theory to solve boundary value problems. And for that, it was important to have the fundamental solutions explicit, and that was the starting point. Then we generalized to this operator theory, well, we didn't proceed to make some particular study, but at least we apply it to this problem, to our problem that was the time-dependent case, and we were successful. Of course, the things, as you said, if the special functions are very specialized, it is a problem then.
Any more questions? So if it's not the case, we thank Milton for the talk. And now we pass to the main speaker of this section, Professor Yuri Gluchko. Let me say some short words about Professor Gluchko. He's one of the most well-known authors in the field of partial fractional differential equations. He has several works, when I mean several, it's a big number of work in this field. He also has works in operational metrics, subdiffusion process, Mittag-Leffler functions, singular kernels, fast diffusion process, Laplacian, and the list is quite huge. He has several papers publishing, most of them in top journals about the fractional calculus and applications. So it's with great pleasure that I introduce Professor Gluchko. He will talk about maximum principle for the fractional partial differential equations and its applications. Please. We are not listening. No, it's...
Eu tenho o microfone desligado.
Sim,
Ok, mas
Professor Yuri.
we are not listening, Professor Gluchko.
Yes. Okay, I'm sorry. Can you see my slides?
Yes, perfectly.
Okay. Well, first of all, I thank the organizers of this very nice special session. for inviting me and for giving me an opportunity to present a part of my research. And I already had a pleasure to work with this group. So we produced some papers, joint papers. And I really enjoyed working with this young and very good groups of mathematicians. You hear it today, some of the presentations, so they developed a lot of very interesting results. And as I already mentioned, the problem now is that easy problems in fractional calculus were already solved. And I was lucky to deal with this topic from more or less from the very beginning. Of course, from the very beginning in the modern history, not from the very beginning, starting from the times of Euler or Lagrange or Leibniz and so on. But still, simple and important problems in fractional calculus have been already considered more or less and more or less solved. And the young generation had to do with more complicated problems, as we have seen today. Why not? Of course, more complicated problems have to be also solved, and they require more advanced techniques and methods. And I'm very glad to see that your group is on a very good way to produce serious and interesting results for these more complicated problems. Well, but let me start with my presentation. I decided to present some of my results regarding the maximum principle for the fractional partial differential equations and some of its applications. And first I start to speak about the maximum principle for a single term, time fractional diffusion equation with the Kaputo derivative. More or less simple case, as I already said. But in the meantime, the research regarding the maximum principles for the fractional differential equations are already advanced, and many other results were obtained, including, for example, maximum principle for the fractional diffusion equation with the so-called general fractional derivative. I will introduce today this object, and even maximum principle for some abstract space and time fractional evolution equations in the Hilbert spaces were already introduced and considered, and a lot of other results. So at the end, I am going to present a short survey of some other results in this field. What is a maximum principle from the mathematical point of view? Roughly speaking, it's more or less a simple statement in the form that if a function satisfies a differential equation or inequality in a certain domain, and this function belongs to a certain space of functions, then it follows that the function achieves its maximum on the boundary of this domain. It's more or less general formulation, abstract formulation of a maximum principle. And maximum principle originates from the physical interpretation of physical processes, like, for example, diffusion processes, because if you consider diffusion in a restricted domain, then of course for the concentration of the diffusing substance, this statement will be true too. So in a sense, the maximum principle is connected with the physical properties of the quantities that are described by some mathematical models in form of some differential equations or inequalities, and have also very, very strong mathematical and physical interpretation. Of course, maximum principle plays a very important role for development of the numerical schemes for numerical solutions for initial boundary value problems for the corresponding equations, because it's very known that the numerical schemes that satisfy the discrete maximum principles, they have certain advantages compared to other discrete schemes for solving numerical solutions of the equations. Well, a very simple example of a statement of this kind is that if the second derivative of a function, of course the function should be differentiable, twice differentiable, and at a certain interval, if the second derivative is greater than 0, and if the function is continuous on the closed interval, then it achieves its maximum value at one of the endpoints of the interval. This statement can be checked immediately with very simple methods of calculus, and it can be considered as a very simple maximum principle. Other examples are more advanced. The literature about the maximum principles for ordinary differential equations and inequalities, and also for partial differential equations and inequalities, is huge. There are many monographs and many books and many papers. So this topic was developed since at least 50, 60 years, very, very extensively. And more or less recently, about 10 or 12 years ago, one started to deal with the maximum principles for the fractional partial differential equations and for the ordinary, of course, fractional ordinary differential equations. So there are publications of both kinds. Historically, more or less, first paper completely devoted to the maximum principle was the paper that was published 2009 with the title Maximum Principle for the Generalized Time Fractional Diffusion Equation. Well, of course, some results of this kind were published in earlier papers already. For example, in some papers by Anatoly Kochubey, who is a very known expert in partial differential equations and in the fractional partial differential equations, he already used some arguments related to the maximum principle, but without explicit formulation of this principle. And there were already some publications by Zacher. It's another expert from Germany in partial differential equations of fractional order, and he used also some arguments of this kind. But still, I would say that starting from this paper, this topic, maximum principles for the fractional differential equations and their applications became very popular. I published several other papers also with some co-authors, but in the meantime, several other authors published, contributed to this topic. So the literature is already very extensive. And in this paper, I started with more or less simple case. So I consider it time fractional diffusion equation of the order alpha between 0 and 1 with the Kaputo fractional derivative. So the left-hand side is the Kaputo fractional derivative that was already defined today. And at the right-hand side, I introduced here an operator, differential operator of the second kind with respect to space in the so-called divergence form. Nowadays, this form is not popular anymore, but this form of the diffusion equation originates from the physical interpretation of the diffusion, and it's derived from the physical interpretation. So I wanted to stress here this connection between the maximum principle and mathematical models for the diffusion processes. Of course, to guarantee the validity of the maximum principle, some conditions had to be posted. For example, the coefficient P should be positive and the coefficient Q should be not negative. And here I provided the definition of the Kaputo fractional derivative. That, of course, was, as already mentioned today, was known long time before Kaputo, this form of the derivative. But well, in mathematics, like everywhere, the names of the objects they not always correspond to the inventors of these objects, but it's just the usual procedure. Well, so okay, of course, an initial condition is posed, and I started with the Dirichlet boundary conditions. The domain omega is an open and bounded domain in the n-dimensional space, and the time variable is also restricted to the finite closed interval from 0 to t. In this paper, I considered solutions in the strong sense. So I required that the solution is twice differentiable with respect to the space variables, and then I required that the solution is a continuous function on the whole interval from 0 to t, because we'll speak about maximum of the function, and this space WT1 guarantees that the Kaputo fractional derivative exists. So it's a space of the functions that are differentiable on the interval from 0 to t, and at the point 0, the functions can have, of course, integrable singularity. No, I mean not the function f, but its derivative can have integrable singularity, and the derivative should be integrable, because if we consider, if we interpret the Kaputo fractional derivative in the strong sense, then we need these conditions. In the meantime, with Masahiro Yamamoto, in another paper with Masahiro Yamamoto, we considered the maximum principle or more general equations of this kind with the Kaputo fractional derivative defined in the weak sense on the fractional Sobolev spaces. So this was already done, but in this first paper I started with the classical case, and the starting point for the maximum principle was the Kaputo fractional derivative. And this extremum principle says that if a function f from a certain space of function, it should be continuous on the interval from 0 to t, and its Kaputo derivative should exist in the classical strong sense. And if this function f attains its maximum over the interval from 0 to t, at the point t0, that belongs to the interval from 0 to t, then we cannot state that the Kaputo fractional derivative at this point t0 is equal to 0, but we can state that it's not negative. In the case alpha is equal to 1, of course, we have the classical result here that the so-called Fermat Theorem, that the function f that is differentiable and continuous on the closed interval, its derivative of the first order is equal to 0 at any point of local maximum and minimum. It's very known results in the classical calculus. But in the fractional case, we can just guarantee this condition. Later on, another stronger inequality for the Kaputo fractional derivative at the maximum point was derived in another publication, this one, and this condition implicates, of course, the first one, the first inequality, because if t0 is a maximum point, then f evaluated at the point t0 minus f at the point 0 is of course greater or equal to 0. But for the maximum principle, for the validity of the maximum principle, this inequality was sufficient. So I didn't need this more strong inequality. Well, this was the first step, and the second step was just to generalize the maximum principle that was very known, already known for the classical diffusion equation. Yeah? And this generalization was luckily straightforward. Yeah? You all worked with fractional calculus already a lot and solved many problems like me. And my experience, and I think it's also your experience, is that in some cases one can generalize the results known for the classical case, for the classical differential equations, for example, to the case of fractional differential equations, more or less straightforward. So you use practically the same method. You make some corresponding changes, and the result is there. But there are some other cases, more complicated cases. I mean, the problem formulations could be simple, but still there are several problems that that don't permit straightforward generalization. Even in the case of this extremum principle. So I mean, if you take the proof classical first order derivative at the maximum point is this result to the fractional case, you will see it's not possible. The direct generalization is not possible. It means that you need here some other arguments, some other approaches. But in the case of the maximum principle, I was lucky here that I just take the classical proof of the maximum principle for the diffusion equation, and it was possible to generalize it immediately, more or less, with the same arguments to the fractional case, of course with appropriate modifications. And the maximum principle says that in the case the source term is not positive on the whole domain, then we have two situations, like in the case of the classical diffusion equations. Then either the solution is also not positive for all times and at all space points, or the second situation is that the solution attains its positive maximum on the boundary of the corresponding domain. And of course, an appropriate minimum principle is also valid. So it was the more or less first formulation of a maximum principle for the fractional differential equations. Well, as I already said, the proof is more or less straightforward. You can check my proof in my papers and compare it with the classical proofs. Of course, some small modifications had to be made, but nothing special in this case. Well, the consequences from the maximum principle are also more or less the same that are known for the classical diffusion equation. So in the case you have a maximum principle, then you can derive some a priori norm as solution norm estimates in the uniform norm, in the maximum norm. Yeah? So you can estimate the solution norm through the norms of the initial value u0, and through the norm of the boundary value v, and through the norm, and this term corresponds to the norm of the source function f. Of course, here you see that we have here a factor that depends on alpha, unlike the classical case, but still these estimates are very similar to those that are known in the case of the classical diffusion equation. And from this norm estimates, it's also more or less standard procedure. One can derive the uniqueness of the solution and so-called continuous dependence of the solution of the problem data. It means that in the case you disturb the source function and the initial value and the boundary value a little bit, then of course the solution is also disturbed, but you can estimate this disturbance in terms of the disturbance of the problem data. So in this case, you can speak about the well-posedness of the fractional diffusion equation in the sense of Adamar, continuous dependence of solution of the problem data. Well, in fact, what I presented here was just the beginning of the big story. Later on, these results were generalized to other kinds of equations and to other kinds of fractional derivatives, and to more general equations, to non-linear equations. I mean, once you derive the maximum principle for the linear equations, you can use the disturbance theory to derive some statements regarding solutions to the nonlinear equations, and you can principles can be derived here, and so on and so on. Yeah. Here some references, as I already said. The first paper was published in 2009, and then several other papers followed. For example, this one, 2010, where I studied not just uniqueness, but also some existence results for equations of this sort. And in the paper, by the way, for sure, all of you are aware of the publications by Professor Gorenflor, Rudolf Gorenflor, who passed away recently. And this was his very last paper, the very last publication of Professor Gorenflor, written jointly with me and with Masahiro Yamamoto. And there we consider a time fractional diffusion equation in the fractional Sobolev spaces. So we generalized the notion of the Kaputo derivative, extended it to the fractional Sobolev spaces, and studied some properties of the fractional diffusion equations. What I presented until now is called in the theory of partial differential equations is known as the so-called weak maximum principle. Strong maximum principle is also known in the theory of the partial differential equations, and this was also derived in a publication by Masahiro Yamamoto and Rundel and Liu. And then in the paper written 2017, we with Masahiro Yamamoto extended the maximum principle for the equations that are more essentially more general than the one I showed you, and also with the solutions in the weak sense. So we consider it here the solutions in the weak sense, and also proved the maximum principle and some consequences. Well, in what follows, I would like to speak about, probably you are aware already of this kind of fractional derivatives, maybe not, but I would recommend you to take a look of this kind of so-called general fractional derivatives and integrals, starting from 2011, yeah, with a paper written by Anatoly Kochubey. This theory started to be developed very extensively during the last time, and several results regarding the fractional differential equations and inverse problems and direct problems and inverse problems were already derived, but there are still a lot of open problems, so you're welcome to contribute. Well, what are the general fractional derivatives? The general fractional derivative of the Kaputo type looks like this. So you have an operator similar to the Kaputo derivative, but you see here a general kernel, kernel K instead of the power law function. And the general fractional derivative of the Riemann-Liouville type is defined like this. So you have practically similar operator, but the order of the integral and derivative is interchanged. So you have first order derivative acting on the convolution integral. Of course, there is a connection between the Kaputo type general fractional derivative and the Riemann-Liouville type general fractional derivative. And of course, these kernels are not arbitrary, Of course, to derive some useful results, you need some conditions on these kernels. And the main condition is that the kernel K should be so-called Sonin kernel. It means that the kernel K should satisfy the Sonin condition. It means that there should exist another function kappa with the properties that the convolution of these two functions is equal to 1. Such functions are called Sonin kernels, and this is called the Sonin condition. Of course, it's not all, because the Sonin condition is also too weak to develop a useful theory of this general fractional integrals and derivatives, but still it's a necessary component. Sonin by himself introduced already about 100 years ago a very large class of the Sonin kernels that are constructed as products of the power functions with some analytical functions. So the function K has the power kernel like the Kaputo fractional derivative, t to the power minus alpha, and the kernel kappa has this factor in the form of the power function t to the power alpha minus 1. It's just a kernel of the Riemann-Liouville fractional integral. But here we have a lot of other possibilities, and of course it's not the only possible class of kernels. It's just an example. Well, the conventional Kaputo and Riemann-Liouville fractional derivatives are particular cases of the general fractional derivative. If you take this power function as a kernel, then of course you recover here the conventional Kaputo derivative and the Riemann-Liouville derivative, the so-called multi-term fractional derivatives that were also mentioned today several times. They all are also particular cases of the general derivatives with the kernels of this kind. And the fractional derivative of the distributed order are also particular cases. Yeah? And a lot of other important operators. Probably you are aware that nowadays in the probability theory, one works with the so-called temporal fractional derivatives. And their kernels are
5 minutes. I'm sorry to interrupt you.
Okay.
But it's only 5 minutes. Okay,
yeah.
thank you.
5 minutes, yeah. So, and their kernels are power law functions multiplied with exponential functions. And these kernels are also particular cases of, say, Sonian kernels, and so on and so on. So, and in the publication by Kochubey, he introduced another class of the Sonian kernels. He required more or less strong conditions on the kernels in the Laplace domain, in particular that the Laplace transform of the kernel K is a Stieltjes function. It's a very strong condition. Stieltjes function can be roughly described as a function that can be represented as a Laplace transform of a completely monotone function restricted to the positive semi-axis, so very strong conditions. And under these conditions, Kochubey could derive some very, very important results regarding the fractional differential equations with the general fractional derivatives. In particular, he could prove that the fractional relaxation equation with the general fractional derivative of this class has a unique solution that is infinitely differentiable and is a completely monotone function. And then he could derive that under the, if the function K satisfies these conditions, then this function K is a Sonian kernel. It means that this condition is satisfied. There exists a function kappa of this sort. And then Kochubey introduced the general fractional integral with the kernel kappa. And this general fractional integral is a right inverse operator to the corresponding derivatives. So everything is provided. And then in the publication that we wrote with Masahiro Yamamoto about 5 years ago, we considered this more or less very general, so-called general diffusion and fractional diffusion equation with the general Kaputo fractional derivative and with the general second order differential operator of with respect to the space variables. D2 is a uniformly elliptic differential operator, and D1 is the operator of the first order. So this equation is, of course, much general, much complicated compared to the equation we started with, but still, Kochubey considered Cauchy problem for the equation of this kind, but with the just with the Laplace operator, and we with Masahiro Yamamoto considered the maximum principle And with the maximum principle, we show uniqueness of solution both in the strong and in the weak senses through some estimates of the general fractional derivative at the maximum points, and then through formulation of the maximum principle. So in fact, we have the same play. So we formulated just some conditions on the kernels K. Of course, some conditions are needed because otherwise it's difficult to work. And then we derived some estimates on the Riemann-Liouville and Kaputo fractional derivatives with the general kernel K at the maximum point 0. And with these estimates, it was possible to derive the maximum principle for this very general differential operator. And then, of course, the same play as before. One can derive the norm estimates. One can derive here the uniqueness of the solution and the continuous dependence of the solution, and so on and so on. Here you see some references. And as I already said, if you are not aware of this object and of this theory, so-called general fractional derivatives and integrals with the general kernels and corresponding equations, you are welcome to look at this theory and contribute. Well, it seems that I spent some time for the talks of my younger colleagues here, but of course they already received very serious results, and of course they needed time to present these results. It's everything okay. What I wanted to mention is that there are many other already cases of equations, more complicated equations, like for example the abstract time and space fractional diffusion equations in this form, where we have not just a differential operator with respect to the space, but a power of positive definite operator minus a, where minus a can be more or less arbitrary, of course not completely arbitrary, and corresponding maximum principle was also derived for this equation. So I skip here the proof that is more or less already complicated compared to the classical proof. So we needed here some ideas.
As soon as you can. I'm sorry to interrupt you.
Yes.
They're asking me.
We used also subordination principle, another important topic. And here on my last 4 slides, I provided an overview of many other publications related to the maximum principle. If you look, if you search in Google for maximum principle for fractional differential equations, you already find a lot of publications. So it's more or less hot topic. Thank you very much for your attention, and questions and comments are welcome. For the details related to these results, of course, you are welcome to consult the publications.
Thank you for your interesting talk, Professor Gluchko. Unfortunately, we do not have time for questions. The organization is asking me to finish the session because they will start a new one at 4 p.m. But we want to thank you for accepting our invitation to present this interesting talk, and you provide us a lot of bibliography, and everybody who wants to study these subjects for sure can contact you for more information. Thank you very much.
It would be my proposal. So of course one should start with reading papers, but in the case of questions, of course, I would be very glad to answer the questions.
Thank you very much. And thank you for all the participants who attend to the sessions. Thank you very much.
Thank you for the organizers once again. Was very nice session. We unfortunately we had too few time like usual during the conferences on place. Of course, one can continue discussions during the coffee breaks and so on, but online is unfortunately not possible. Let's hope that we meet each other in the next future by one or another conference in place, not online anymore. Yeah. Thank you.
Thank you, Professor Yuri.
Yeah.
Yuri.
Bye.
Bye.
Bye bye.
Bye.
Bye bye.
We
Bye
keep
bye.
in touch.
All the best. All the
All the
best.
best.
All the best
We
for
keep
you.
in touch. We keep in touch.
We keep in
Yeah?
touch.
Okay.
We keep in touch.
See you soon.